All right, so this is going to be your video on basically the differences between charging by induction and charging by conduction. The vast majority of this worksheet, honestly, is relatively straightforward if we read through all of the information presented. That is historically, though, one of the more challenging things. Students tend to not read it, and they just try to start drawing things, and they're not paying attention to this whole part right here, where I give you all of the directions for exactly what to draw, where to draw it, and how to draw it, or what's actually happening. So I wanted to make a quick video, at least walking you through it so that you can see what's actually happening. This first example is going to be made through what we call conduction, because you're making physical contact with this rubber charging rod. And remember, all that's occurring in any of these situations, any of these scenarios, any of these circumstances is electrons in a highly concentrated region, kind of like the weather map thing we talked about, or high gravitational potential, low gravitational potential, hot to cold things. Doesn't matter what example we want to use. These electrons are on a highly concentrated, negatively charged rubber piece of rubber, and when they're given the option to travel to something that's a little bit more electrically neutral, they totally will. And all of those electrons will start to get deposited on this new, basically, real estate, right? It's kind of like the suburbs, right? The cities get really, really, really crowded, and people start spreading out further and further away, and the suburbs move further and further out from the city, right? As people move progressively further away. Well, the electrons do the same thing. And so in this particular case, this first example right here is an example of transferring negative electrical charge from a charged object onto a neutral object. Then the whole object now simply has more electrical charges right here than it started with, right? It started off as neutral, and now it has this excess of electrons. Now, the way some older textbooks or diagrams might describe this, second version is if the charged rod, the rubber rod, was charged positively, meaning it had a lack of electrons. Some physics textbooks or really old sources like from Benjamin Franklin, or the 100 years in between Ben Franklin and when we discovered what the structure of an atom was, will have positive charges moving back and forth. It's very important that we recognize that that does not actually happen. If you have a positively charged, in this case rubber rod, what that means is that it has a lack of electrons. It does not have excess positive electron or positive protons. It does not have excess positive charges. It has a lack of electrons. It lost some of the electrons. And so this object that we're dealing with here, this sphere, is probably going to start off as electrically neutral, right? It's going to have as many positive charges as it has negative charges. I've tried to represent that. And what's going to happen is those electrons are going to move from the neutral object to the object that is lacking electrons. And those electrons will transfer up into there. They'll reach equilibrium, right? If I've got 4 extra negative charges on this sphere, then 2 of those 4 will go to the charging rod, and those electrons will be as far apart from each other as they possibly can. They'll space themselves out as equally as possible. And you're going to get, for the most part, a positively charged sphere that's left over. You might have 1 or 2 negative charges that are still on it, right? Because not all of those electrons transferred, but you did have a transfer of electrons, and now the vast majority of that object is positively charged. You can do the same thing with rubbing a balloon on your head. If you ever did this as a child, it's a cool little party trick. You could totally do it. You rub the balloon on your head. As a result, the balloon itself loses electrons. It becomes positively charged. And if the balloon itself, right, because I explained that here, if the balloon itself is then placed on the wall, what's happening with that positive charge is normally the positives and negatives in the wall, they're perfectly staggered, right? For every positive, there's a negative. Well, what you're doing by putting this very large positive charge on it is you're basically causing the electrons in the wall to shift and to move. And you lose this pattern that you would have normally had of alternating positive and negative charges. And it only happens right there near the wall, near the balloon. And once you get further away, the wall goes back to being electrically neutral. And so it's that temporary reshuffling of the electrons, or the electrons in the wall temporarily relocate. And there's actually an attractive force between those two, and you can get the balloon to stick to the wall in that particular regard. So that's all number 2 is trying to get across, right? That's I guess you could call it inducing a charge, because you're not really transferring too much. Eventually it will fall because the electrons will slowly trickle into the balloon and they'll both become neutral. Number three, this is how you can induce a permanent charge on an object. So remember, induction does not require physical contact. We're not actually taking this rod right here, despite its positive charge, and making contact with sphere A in any way, shape, or form. We start with a neutral pair of objects. Both of these spheres have protons. Both of these spheres have electrons. When we bring this positively charged object nearby, you're shuffling about those electrons. You're pulling all of the extra electrons that you had from sphere B over to sphere A. Those electrons are going to move from sphere B over to sphere A because they're in contact. So because they're in contact, those electrons migrate over to sphere B, from sphere B to sphere A, and then you separate them. And those electrons are basically landlocked. They're stuck there on sphere A with no way to get back to sphere B. Now sphere B is separated from the electrons it originally had, and what you have done, once these electrons are allowed to, reshuffle on that new surface, you've got more negative charges on sphere A than you had before, and you have fewer charges on sphere B than you had before. So what is the charge on sphere B in step B? It's going to be a partial, not complete, but a partial positive charge, because those electrons migrated over to sphere A when that positive charge was there. Opposites attract. And the charge on sphere A in step C is negative, and the charge on sphere B in step C is positive. They retain those opposite charges, and until they make contact with each other or something else, those charges will remain. It is a way to permanently relocate electrons. By inducing a charge, notice there was still no contact being made here. Right? I want to put an X there. No contact being made. It's silly. It looks ridiculous. My point is there's no contact being made. And that's what we call induction. You've induced a charge without making physical contact. Number 4, you can actually discharge an object by doing exactly this. Initially, by using induction, this object, this sphere, would have likely been electrically neutral. So I drew 4 positives and 4 negatives. And if you bring a negatively charged object nearby, you can induce a separation of those charges. The electrons, literally, the positives don't move, but the electrons will literally migrate over to the other side of the sphere to try and get away from the other electrons that are also on this rod. What you're doing here is the same thing we did with the Van de Graaff generator. You are giving those electrons an escape route. You're grounding, literally. This is an example of grounding. I have that word up there somewhere in that massive paragraph. Where is it? There it is. Grounding, like the ground wire of your electrical plugs that you have at home, the third wire. You're grounding this by giving the electrons an extra path out. Because those electrons had an extra path out, now you'll notice there's absolutely no more excess electrons left on the sphere at all. They have traveled from one location on that sphere in step C through your arm, and now we're just gone. I've gone literally into the ground. You can do the same thing down here with a positive charge. I'm going to draw a lot fewer charges because I'm lazy and I want to get this done with so I can post this. But if we've got equal numbers, start with the neutral object in step A, you bring a positive charge nearby, your negative charges will line themselves up on the left-hand side, attracted to the positive charge that's there. That leaves a bunch of exposed protons on the far right. Notice we're not doing any additional stuff here. What's happening isn't, actually this arrow's in the wrong direction, those positive charges aren't moving. What's happening is there's a distinct lack of positive or negative charges over here on the right hand side. and that positive charge is going to be pulling electrons from you to fill that void. Quite literally, when you remove your hand and all is said and done, now you've got more negative charges on this object than you had before. That is your, well, over here it should still be inducing that charge. So let's make sure we represent that. But you've now picked up another negative charge or two over on this side, and your total charges are significantly more negative than they were before. That's really all this is. That's induction and conduction. Remember, the big deal between those two, really the two main ideas of this entire worksheet, this entire quick video that I've just done, is electrons are the only thing that are moving. That's it. That's all. It's all electrons. And conduction requires physical contact. Induction does not require physical contact. That's really it.